Yep, I am live. That is crazy, I guess. Just let me check. Yep, I am live and we can begin. And yesterday we were doing some crazy things. We were learning about SIMD instructions, which are in itself crazy instructions. Yep, inside floating point. These that yesterday we came to know that there are different processing units which are designed for different things. For example, there is a processing unit which can operate, which can perform a same instruction, for example, fetching, storing, addition, subtraction, multiplication, division on different data points at the same time, on multiple data points at the same time. That is, I can add four pairs of numbers at the same time. And for that, I have different instructions and different processors and different registers to do that. And commonly, these different processing units are inside the main processor itself. But in the past, in older days, we had vector floating point coprocessor. And here, vector means a set of different values, and floating points means these units specialize in operating floating point numbers and multiple of them. That is why it is vector and floating point. And in the past, we used to have the separate unit which does these calculations, which is especially designed to do these calculations, used to be external part which is outside the main processor, and the main processor sends the control unit sends instructions to perform the SIMD, single instruction multiple data instructions to that external unit and then used to get the output. But in today's days, we have that external unit inside the processor itself, and that is crazy. And we have two types of these. First is floating point unit, which specializes in dealing with floating point numbers. That is numbers which have a radix, which have a radix point at some place in them, and there is a neon unit which implements single instruction multiple data sets. That is, it performs a single instruction on multiple pairs of data at the same time. Instead of adding just two numbers and then storing them into a third register, I can add, let's say, four pairs, that is eight numbers, and get four different results and store them into a place or whatever. And neon is one of the ways we can implement single instruction multiple data set things. And here we are. These registers have their own things, have their own processing units, have their own registers like this. V stand for vector here. That is just crazy. Now, floating point overview. Historically, ARM has implemented floating point operations by adding a coprocessor to the CPU. The coprocessor extends the instruction set that is supported by the system. There are five major revisions of the ARM floating point instruction set and coprocessor. Vector floating point version 1. Vector floating point coprocessor version 1 is obsolete. That is, it is out of production now. It is not uh, uh, it is not implemented anymore. Vector floating point 2, an optional extension to the ARM v5 and v6 processors. Uh, VFP version 2 has 16 64-bit floating point unit registers. So it has 16 64-bit. We don't have to remember that. Floating point version 3, an optimal extension to the ARM v7, that is and the one before the latest version of ARM. Latest is V8 processors. It is backward compatible with V2, except that it cannot track floating point exceptions. Okay, V3 D32. D is double, that is 64. Ah, D means just double. Has 32 64-bit FPU registers. Some processors have V3 D16, which supports only 16 64 floating point unit registers. V3 adds several new instructions to the vector floating point instruction set. Okay, and then we have V4 implemented on Core Cortex Core Cortex V7 processors. V4 has 32 64-bit FPUs registers. It adds both half precision extensions and multiply accumulate instructions to the features of V3. Some processors have VF VFP version 4 D16, which supports only 16 64-bit FPUs. Okay, I do not understand what this part means. What is Cortex on some Cortex? Okay. Neon defines single instruction multiple dataset extensions to the instruction set. Neon supports the floating point instruction set along with along with integer operations. Okay, we can do floating point things on this Neon extension and also integer operations. The Neon instruction set allows for a single instruction to perform operations on multiple pieces of data at the same time. Okay, on some Cortex of ARM V7 processor. What does Cortex of ARM V7 processor mean? What does it mean? In the cortex of ARM V7 processors, the term cortex refers to the family of processor cores designed by ARM Holdings. Advanced risk machines, or earlier it was Acorn Risk Machines Holdings. ARM licenses these core designs to various semiconductor companies. ARM licenses these core designs to various semiconductor companies which integrate them into their system on chip SoC system on chip designs like M1. ARM V7. Wait. In the context of ARM V7 processors, the term Cortex refers to the family of CPU cores. What does a family of CPU cores mean? Designed by ARM Holdings. Family of CPU cores designed by ARM Holdings. So they design them. Isn't that just the instruction set? ARM licenses these core designs. Okay. Well, there is ARM instruction set, and then there is how do you implement that instruction set. So ARM has an instruction set, and then they have Cortex, which is a family of CPU core designs which can be used to implement that instruction set. And that design is a system on chip design. That is, the whole system is on the chip. That is the processor, the RAM, and yeah, the processor, RAM, GPU, everything is on a single chip, except the, of course, peripheral devices and the hardware storage, external secondary storage. ARM v7 is an architecture specification. Yep. And Cortex A, Cortex R, and Cortex M are core implementations that conform to this architecture. Yep. These cores are optimized for different types of applications. Okay. Cortex E series application processors used in smartphone, tablets, and general purpose computings and supports features like virtual memory, multimedia processing, and high performance. Virtual memory, multimedia processing, and high performance. Okay, example, these are used in Oh, these are used in phones, tablets, and general purpose computing. High performance, virtual memory, multimedia processing. Okay. Real-time processors are Cortex are okay, used in automotive systems, industrial automation, and medical devices. Okay, because you want medical devices to work in real time. If the patient is dying right now, you want to know it right now. Designed for real-time performance, high reliability, and low latency. Low latency is real-time performance, I guess. Examples: Core R4 and R is just real-time. M series microcontrollers. What are microcontrollers? Used in low-power embedded systems, low-power embedded systems, IoT devices, and wearables like a watch. Optimized for low power consumption, design, deterministic execution, and simple design. Okay, so when you hear Cortex in ARM v7, it generally refers to the specific processor cores within the Cortex A that implements the v7 instruction set. Okay, so not okay. So, and the ARM company has two products. First is the ARM instruction set architecture, I say, and different companies can design their own, and different companies can design their own processors and then manufacture them, which implements this ISA. And then ARM also provides a processor, a core and design so that uh, companies companies, if they don't want to, then they if they don't want to, then they don't have to design a processor from scratch that implements in their ARM ISA. They can instead use the Cortex designed by ARM and manufacture their processor on that design, right? I guess that is exactly. Yes, exactly. ARM operates on licensing models and offers two main types of products. ARM instruction set architecture. ARM develops and maintains the ARM v7, v8, and V got M9. We have v9 now, etc. etc. That is, we might have more in the future. RISC-V is a thing, I guess. Instruction sets. Companies can design their own processors that implement these ISAs. Example, Apple's M1 and Qualcomm's Snapdragon. Fucking hell. ARM processor core designs ARM processor core designs, Cortex, Neoverse, etc. ARM provides pre-designed CPU cores like Cortex ARM and Neoverse. Companies can license these designs instead of designing a CPU from scratch. They take the design, manufacture it on their own silicon, and integrate it into their chips. Example: Qualcomm, MediaTek, and Samsung use Cortex designs in their smartphone processors instead of designing their own CPUs. Qualcomm uses Cortex, but it also Qualcomm's Snapdragon uses, but Qualcomm might have other processors which are based on the Cortex designs. Two types of ARM licenses: ISA license, Apple, Qualcomm, Amazon. allows companies to design custom CPUs that are ARM ISA compatible. Example, Apple's M series and use ARM V8, V9 ISA, but the core are Apple's custom designed, not Cortex. Core license, Cortex, Neoverse, etc. Example, MediaTek, Samsung, Rock chip. But why does Samsung? Well, Samsung phones are not the only things that Samsung designs, and phones use Snapdragon chips, but Samsung also designs and manufactures tanks, ships. That is crazy, and there it might use the Cortex design for its processors. You do not need a, well, you can use a Snapdragon chip in a tank. Well, okay, you can use if you want to. Companies can license ARM's ready-made Cortex design and integrate them into their system on chips. I guess system on chips is the thing now, but if system on chips, then you cannot update your RAM, but can and yes, Cortex design is mostly used for phones. So can you not update your RAM in a phone? That is a good question. I guess I haven't thought about it before. Snapdragon processors use Cortex cores, others use custom cores. So ARM doesn't manufacture chips itself. It licenses the ISA and CPU designs to others who manufacture their own chips. Yes, the Cortex design is a system on chip, so that and it is mostly used in phones. So does that mean Cortex based processors processors can't be updated in their RAM, can't get their RAM updated because it is um, integrated on the chip. Well, at least it is on Mac M1. Not exactly. Cortex is not an SoC itself. It is a CPU core design that companies use inside their SoCs, which companies use inside their SoCs. So, okay. Cortex is only the core design. It does not specify the RAM that you are using. So, yeah, people can use it to implement to integrate cores onto the chips, and they can think about RAM on their own, where to integrate it on their own. Whether the RAM is upgradable or not depends on how the final SoC is designed. Not so SoC does not specify that the system also includes the RAM on the chip. Cortex versus SoC. Cortex refers to just CPU cores designed by ARM. SoC, system on chip, is a complete chip that integrates CPU, GPU, memory controller, other peripherals. Okay, most smartphones use Cortex-based SoC, example Snapdragon, Exynos, MediaTek, and these typically have RAM soldered externally on the motherboard, not integrated on the chip itself. Okay. You can't upgrade RAM in most smartphones, not because of Cortex, but because the SoC and motherboard design prevent it. Does Cortex-based hardware always have fixed RAM? No. Cortex uses Cortex cores are used in many devices, not just phones. Smartphone, tablets, RAM is usually soldered, not upgradable. Single board computers, Raspberry Pi, RAM is usually fixed. Fixed, but I cannot improve RAM in my Raspberry Pi. I will have to get a Raspberry Pi. Laptops ARM-based, like Apple M1, RAM is often integrated into the SoC. Example, RAM's unified memory. Server workstations, ARM Cortex or newer sports. RAM is upgradable via separate DIMM slots, just like x86 systems take away. Cortex is not an SoC, just a CPU core design that makes sense. Whether RAM is upgradable depends on the SoC and system design, and not on Cortex itself. Okay, many ARM-based servers and laptops have upgradable RAM, while phones and tablets usually don't. So, okay, um, you said that Snapdragon, that Qualcomm has its own design for the ARM ISA, but you also said that it uses Cortex at some places. So why is that? Let's see. Great question. Qualcomm does both. It designs its own custom ARM CPUs, but also uses ARM's Cortex in some chips. The reason comes down to cost, performance, and time to market trade-offs. Time to market. Okay, that is a new term. Qualcomm's two approaches to ARM CPUs: custom ARM CPUs, ISA's license. ISA license. Qualcomm has ARM ISA license, which allows it to design its own custom CPU cores that are ARM compatible. Example, Cryptos, where is used in Snapdragon flagship chips. Oh, these are designs. Scorpion cores. These core are core designs are used in Snapdragon chip. Okay, these cores aim to be more powerful and efficient in the than ARM's standard Cortex cores. Okay, using Cortex cores core license in low end or mid-range chips, Qualcomm sometimes licenses ARM's ready-made Cortex cores instead of designing its own. This is cheaper and faster than developing custom CPU designs, because you have to maintain your CPU design with the running ARM ISA, and that takes money and effort. Instead, you can just take the design that they are offering, which is already compatible with their latest ISA. That makes sense. Example is Snapdragon S77 and some Snapdragon 8XX, 7XX, and 8XX chips use Cortex cores like Cortex this and this. Okay, why does Qualcomm mix both approaches? High-end flagships, custom cores. Snapdragon 8 Gen 3 has custom designed cryo cryo cores and faster development and lower research and development costs if you are using Cortex cores. For example, Snapdragon 7 Gen 2 uses ARM Cortex cores. Other companies are doing the same. Apple uses a full custom ARM ISA for its M and A chips. Samsung previously made custom cores, Exynos M series, but now uses Cortex cores. So Samsung makes its own processors, doesn't it use Snapdragon? MediaTek primarily uses ARM Cortex in its Dimensity Helio chips. Qualcomm designs. Okay, so does Samsung uses manufactures and designs and manufactures its own processors and not use the market standard Snapdragon chips, or does it uh, use Snapdragon but only in its phones and uses and manufactures its own processors for its other products like tanks and ships. Uh, Samsung does both. It designs and manufactures its own processors, but also uses Qualcomm's Snapdragon chips in many of its devices. Here's how it works. Samsung's own processor, Exynos, custom ARM. The design and manufacture. Samsung designs and manufactures Exynos chips under its Samsung System LSI division. LSI life sucks intensely. Xenos processors are used in smartphones, tablets, wearables, and IoT devices. Okay, Xenos 2400, 2200 used in Galaxy S24 and S22. That in some regions, manufacturing Samsung fabricates Xenos chips at its Samsung foundry, just like manufacturers, just like it manufactures chips for other companies like Qualcomm, Nvidia, and Apple, like it manufactures. Okay. Samsung uses Qualcomm Snapdragon in some devices. And Samsung often uses Qualcomm Snapdragon chips in its flagship phones in markets like the US and China. This is because Snapdragon chips usually perform better in areas like high power efficiency and modern technology. Example, S24 Ultra US has a Snapdragon 3 chip, but S24 Ultra Europe and India has a Exynos chip. Okay, even though the model of the phone is same, the processor is totally different. The ISA is same. ISA is ARM in both, but the processor here it is in US it is Snapdragon 8 Gen 3 and in Europe it is Exynos 2400. Hmm. Hmm. Samsung also manufactures chips for other users. Samsung makes chips for industrial, automotive, and military applications. Automotive processors, EDAS, infotainment, infotainment. Okay. AI processors, IoT, and security chips. It has not publicly disclosed making chips for tanks or warships, but it does produce semiconductors like defense-related semiconductors like secure processors for military communication. Samsung Foundry manufactures chips for others. Samsung not only makes Xinos but also manufactures chips for other companies. Clients like Qualcomm, Nvidia, AMD, and even Apple. Older A series chips before Apple moved to TSMC. Fuck, I read what does TSMC mean. CS chips. To say much chips. Um, okay. So, Samsung Galaxy S24 Ultra comes with different processors um, based on region, even though the model is same. And doesn't this affect the um, performance and uh, performance efficiency and speed is performance and others due to this change? Yes, the Samsung S24 Ultra and other Galaxy S series phones have different processors based on region. Does this lead to variations in performance, efficiency, and other factors? This has been a long-standing practice by Samsung, and it does come with both advantages and drawbacks. How the processor is split works in the S24 Ultra, US, Canada, China, and South Korea have Snapdragon chips, and Europe, India, rest of the world. Europe, India, rest of the world is also US, contains Exynos 2400. Samsung calls the Snapdragon Gen 3 for Galaxy because it is a slightly overclocked version made exclusively for Samsung. Samsung calls the okay calls the Snapdragon 8 Gen 3 for Galaxy. It is specifically designed by Qualcomm for Galaxy because it is a slightly overclocked version made exclusively for Samsung. Overclocked means it can do more in a given second. The state of the processor can change more times. High clock speed means uh, the transistors can switch their state more quickly. Differences between Exynos 24 and Snapdragon 8 Gen 3. CPU 10 cores, 8 cores. Manufacturing 4 nanometer Samsung Foundry TSMC. TSMC Semiconductor Manufacturing Company. TSMC from Taiwan Semiconductor Manufacturer Company. Okay. No. Taiwan TSMC, Taiwan Semiconductor Manufacturer Company. Better efficiency. In GPU, it has these AMD, RDNA, some GPUs, and this has Adreno 750 GPU. Power efficiency worse than Snapdragon, more power efficient. Snapdragon is more power efficient. Okay, and AI and ISP performance good but slightly behind, leading in AI processing. Modem Samsung Exynos modem Qualcomm X75 better connectivity. Verdict historically, Snapdragon variants have outperformed Zyno models, especially in efficiency, thermal, and GPU power. However, in the S24 series, Zynos 24 has improved significantly, reducing the performance gap. Does this affect the user experience? Performance difference? Snapdragon models usually have better sustained performance under heavy workloads. Zynos models may throttle slightly faster under prolonged gaming or CPU tasks. Okay, battery life and efficiency. Snapdragon's Taiwan Semiconductor Manufacturing Company 4 nanometer process is more efficient, leading to better battery life. And Exynos 2400 uses Samsung's 4 nanometer process, which isn't as power efficient, but the gap has narrowed. Gaming Snapdragon have historically been stronger, and Exynos, which has improved but still lacks is cameras. Snapdragon Qualcomm has superior ISP, which leads to better HDR and low light photography. Xanos is catching up, but is still lagging. Modern, so it seems like Xanos is much better. Sorry, Xanos is not as good as Snapdragon. So why does Samsung do this? Cost and supply. Samsung wants to use its own Xanos chips to reduce reliance on Qualcomm and lower costs. Qualcomm charges high license fees, so using Exynos helps Samsung increase profit margins. Samsung chips, Samsung chip shortages and production flexibility. If Samsung only relied on Qualcomm, any supply chain issue could cause delays. Having two sources, Exynos and Snapdragon, makes production more flexible. Branding and future goals. Samsung wants to compete with Apple by controlling more of its own hardware. Over time, Samsung aims to phase out Qualcomm completely and use Zynos globally. Ah, okay. which is a better variant. If you buy in US or South Korea, you get a better variant with a Snapdragon 8 chip. If you are in India, Europe, or other regions of the world, you get Exynos 2400, which is improved significantly but is slightly behind Samsung Snapdragon in efficiency. For most users, the difference is small unless you care about gaming, battery life, or extreme performance. If you do, Snapdragon is still the better option. Okay, that makes some things clear. And why did I started looking started searching on ChatGPT? Because I wanted to know the meaning of this word cortex. Okay, now I know, and we can begin. We can move forward. And how much time has it been? It has only been 25 minutes. We got this. AArch64 integrates floating point and SIMD more tightly into the processor core while still maintaining instructions that are similar to the original FP and Neon instruction set. Integrates floating point and SIMD tightly more into the processor core. Okay. Figure 9.1 shows the 32 AArch64 integer registers and the additional registers provided by the AArch64 advanced SIMD instruction set as shown in figure 9.2. As shown in figure 9.2, AArch64 FP Neon instruction provide the ability to view register as 32 quadruple word, 32 quadruple word, Q, 32, is set as 32 quadruple word 128 registers named Q0 to Q31 or 32 double word 64-bit registers named D0 through D31 or as 32 single word is 32-bit registers named S0 through S31. Each register can also be referred to as a half word register H0 through H31 or a byte register B0 through B31. Yay! Half word or a byte register. B0 through B31. Half word is 32 and a half word is 16 and a byte is 8. Okay. Additionally, proportions of each registers can be referred to by using a subscript notation such as this, which means the first 64 bits and what does one mean, which refers to the upper 64 bits of register V1. This V1 means the name of the register. 64, how many bits I want to access, and what does 1 and F mean? I will know in due time. The processor supports IEEE single precision and double precision numbers. Each of the first 16 double precision registers can be used to store either 164-bit number or 32-bit numbers. For example, double precision register D0 may also be referred to as a single precision register S0 and S1. Registers D16 through D31 cannot be used as single precision registers using the basic FP instructions. Okay, the vector floating point instruction set added about 28 new instructions to the ARM. About 28 new instructions were added to the ARM instruction set. The exact number of VFP instructions depend on the specific version of the VFP cores. Coprocessors AArch64 supports instruction equivalent to VFV4 instruction set. There are 23 basic instructions in the Arch FP Neon instruction set, but some have several variations in instructions provided to transfer floating point values between FP registers. What does this mean that AArch64 supports instructions equivalent to VFP VFP version 4 instruction set? VFP version 4 instruction set. defines the instructions that to be used in vector floating point register. What does it mean that ARM64 supports instructions equivalent to that? Yeah, GVD. What was the line? This line. Or does this mean? Does it mean that ARM64 supports instructions equivalent to that? Does it mean that I can use some AArch64 instructions to perform actions in the vector floating point unit or and the neon unit SIMD unit uh, and if this were not the case, is it generally not this were not the case, then are these extension instructions performed by writing a separate program, but with AArch64 support we don't have to do that and can integrate the vector floating point and neon instructions within a single program of AArch64 assembly. Let's see. I don't know. Yes, you have got the right idea. Let's break this down step by step. What does AArch64 supports? VFP vector floating point version 4 instruction mean? The AArch64 The AArch64 ARM architecture includes instructions that are equivalent to version vector floating point version 4. This means you can use AArch64 instructions to perform vector floating point operations without needing separate VFP specific instructions. The same applies to Neon SIMD operations, which are integrated into ARM64. VFP and Neon and ARch64 in older ARM architectures. This VFP vector floating point unit was used for scalar floating point operations. SIMD unit was used for vectorized operations, processing multiple values in parallel. VFP and Neon had separate instruction sets and using them required explicitly enabling these extensions. Okay, explicitly enabling these extensions. ARM-V8 and later, VFP and Neon are now fully integrated into the core ISA. Okay, it is not an extension of the core, it is the core, part of the core. No need for separate programs or specific handling. You can mix a normal integer float point and SIMD instructions in a single AArch64 assembly program. Registers are unified. AArch64 uses 32 SIMD FP registers, these 128 bit replacing the separate VFP and Neon registers from AArch64. Registers are unified. Arch uses 32 SIMD FP registers V0 to V31, 128-bit each, replacing the separate VFP and neon registers from AArch32. Okay, okay, the registers for SIMD and FP are same. Hmm. What if AArch64 didn't have VFP neon support? If AArch64 didn't support these instructions, you would have to write separate assembly routines using VFP and neon in AArch32 mode. Use software emulators for floating point operations, which would be much slower. Manually offload floating point and SMD computation to separate coprocessors or accelerators. With R64 built-in support, you don't have to do this anymore. Floating point and SIMD operations are part of the main instruction set. Okay, you can use floating point VFP and neon instructions in R64 assembly. Yes, you can use floating point and SIMD neon instructions directly in R64 assembly. Here are some examples. Float move something, and then float move something, and then float add. Neon SIMD, do I before. Okay, but now I want to know. So the new AArch64 V8 has two sets of registers. First, the general purpose 64 third, general purpose 3264 bit regis, registers, and also 32 128 bit vector registers. Is that correct? Seems to be yes, exactly. RM64, ARCH64, V8A. A means application. Has two separate sets of registers. General purpose registers used for integral and pointer operations. So that is why they are called general registers, because you do a lot of shit with them. Vector, SIMD, and floating point registers, V registers, used for floating point and SIMD operations. General purpose registers, GPR, named X0 through 30, and 64-bit operations and 32-bit operations. Size 32 registers, each 64-bit. Special registers, frame pointer 29, link register is the 30th, and 31 acts as the stack pointer. Oh, or zero register depending on the instruction. Okay. Vector registers. V registers, well, I can see, let's say register.s. I can text, I can see the value in the 31st register, what it is. In the text, global main, don't have to do that, but okay, main, and then move mm, 0 into the 0th register, the value of the 31st register, and then just return. That is all. Clang register.s and output dot out and dot slash out, and echo to see the exit code, dollar question mark, or is it question dollar mark, dot slash out, echo question mark, dollar sign. Okay, dot slash out, echo dollar sign question mark. Okay, it is due to some reason containing zero. Okay, it depends on the processor, right? Yeah. Vector registers, V registers, named V0 through V31, size 32. There are 32 registers, each 128 bit. white, used for floating point and SIMD operations, aliased sub registers. D double word, that is 128-bit. Nope, single word, double word. Yeah, not 128. Double word is 64-bit. Then I have single word 32-bit, and then half a word which is 16, and then a byte. Different interpretations for SIMD data. Summary: general purpose registers and vector registers. This is 30, 32, 64-bit, 128-bit, integer, and floating point. Ah, okay. Okay. Transfer floating point values between FP co-processor registers and main memory. Transfer 32-bit values between the FP co-processor registers and the ARM integer registers. Perform addition, subtraction, multiplication, and division involving two source registers and a destination register. Two source registers and a destination registers. Yep. Compute the square root of a value. That is crazy if I can do that. Compute a square root of a value. That is just crazy. Perform combined multiply accumulate operations. Okay. Perform conversions between various integer fixed point. My bad. I don't know why I want to sleep. Perform conversions between various integer fixed point and floating point representations and compare floating point values. Okay, that is just crazy. What is this? Bits in register usage rules. As with the integer registers, there are rules for using FP registers. These rules are a convention, and following the convention ensures interpretability between code written by different programmers and compilers. A register V0 through V7 are volatile, as in general purpose registers. They are used for passing floating point arguments into a subroutine or storing local variables. Register V0 is also used for returning the result of a function if the result is a floating point number. That also makes sense. That is the same as a general purpose register. Registers V8 through V15 are non-volatile, which meaning that the contents of these registers must be preserved across subroutine calls. If the subroutine uses these registers, their content must be first saved somewhere, usually on the stack, and restored before the subroutine returns. Registers 16 through 31 are also considered volatile and can be used for local variables and temporary variables. Okay, so these are the same rules as the rules which apply for general purpose registers. In addition to the FPCR, FPCR, what is FPCR? Fractional floating point. CR, R is registers. What is C? In addition to the FPCR, what is FPCR? Floating point CR. Shit, I refreshed. Load, restore, single register, floating point. There are a lot of instructions to be read. FPCR, FPCR, ARM, full form, floating point control register. Like it must be one of them. FPCR, FPCR, and FPSR, stack register. Floating point control register and floating point stack register. In addition to the FPCR, all FP Neon implementations contain at least two additional system registers. Okay, the floating point system ID FPSID is a read-only register whose value indicate which floating point neon implementation is being provided. The contents of the FPSID can be transferred to an ARM integer register, then examined to determine which FP neon version is available. There is also floating point exception register, 2 bits of the exception register, FPXC, not R, EXC, somehow, 2 bits of the exception register provides system level status and control. The remaining bits of this register are defined by the sub-architecture. These additional system registers should not be accessed by user applications. Okay, I will not let them be accessed by user applications. Floating point control and status registers. FPCR, floating point control register, allows the programmer to control how floating point operations are performed. The layout of the neon floating point control register is shown in figure 9.3. The meaning of each field is as below. This is the register. It seems like it is only 32-bit long, and it is actually only 32 bits long. And the 20 from 26th to 22nd bit, we have some special bits, and the 19th bit is also special. AHP, alternate half precision control bit. 0 use AIEEE half precision format, and 1 use alternative half precision format. Okay, alternate half precision control bit, alternate half precision DN, default in NaN enable, not a number. Disable default NaN mode. NaN operands, not number operands, propagate through to the output of a floating point operation. Enable default NaN mode. Any operation involving one or more NaNs, return the default NaN. Return the default NaN, whatever is the default in NaN. Flush to zero enable. Disable flush to zero mode. Enable flush to zero mode. That actually makes sense. No, no, it doesn't. Flush to zero mode replaces subnormal numbers with zero. This does not comply with IEEE standard, but may increase performance. Default subnormal values with zeros. Okay, RM mode, rounding mode, 0 round to nearest round number, round to nearest plus infinity, round to nearest minus infinity, plus and minus, round to towards zero. Okay, FZ16 flush to zero mode control bit for half precision data processing instructions. Disable flush to zero mode for half precision. Enable flush to zero mode for half precision. Okay, this deals with flush and half precision. Half precision uses 16 bits, so the 16 signifies that, I think, and EF just means I don't know, flush, yep, I guess. The FPCR can be read into an AArch64 system register, modified and written back to change the settings. My bad. Code sequence for changing settings is as follows. Register S MSR, select clear with FPCR to X T, read FPCR into X and set clear bits. Write XT to FP. Okay, and at this point I clear the bits that I want to, and then I move it back to FPCR. The floating point status register allows the programmer to view information about the status of the floating point unit. The FPSR is shown in 9.4 My actual bad. Figure 9.4, the meaning of each field is as follows. Where is figure 9.4? Yep. Where the floating point control register FPCR has been divided to shit. Match a lot of things. Negative. The flag is set by V compare if the processor is running. V compare. And there is a space between V and C. Nope, nah, there is not. If the processor is running in AArch32 mode, AArch64 comparisons set the piece.n, p-state.n flag directly. AArch64 comparisons. AArch64 comparisons set the p-state n flag directly. Okay. The zeroth flag is set by the v compare if the processor is running in AArch32 mode. AArch64 comparisons set the n flag directly. Now, figure 9.4, here we have it, and here we have C and V overflow carry. Flag is set by V compare if the processor is running in this, and R64, and then V is for overflow. QC, the saturation cumulative flag. Saturation cumulative flag is set to 1 by saturating instructions. If saturation has occurred, this will be explained in more detail in chapter number 10. I hope it does. Hey, it has been 1 hour, and why the heck do I feel sleepy? That is not an acceptable, not an acceptable anything, right? IDC, the input subnormal cumulative flag, is to set 1 when IDE condition has occurred. Okay, these are making less and less sense, and I guess will be more clear when I am writing code, or I can right now go to ChatGPT and ask about them and make things more clear. And I would also like to make these condition flags and program states registers more clear in normal general purpose unit. That would also help me. The FPSR can be read into AArch64 system register and examined. The instructions for reading the FPSR is as follows. FPSR is load store instructions here. FPSR bits can also be set by moving data from an integer register to FPSR. This allows the program to clear this exception. Why are you not telling us what does these mean? MRS and MSR. Load store. Let's go there. The FP instruction set provides several instructions for moving data between memory and FP registers. There are instructions for loading and storing single and double precision registers, and for moving multiple registers to or from memory. All of the load and store instructions require a memory address to be one of ARM64 integer registers. Oh, they want the memory address to be one of ARM64 integer registers. That is the general purpose registers. The available memory addressing mode are identical to the integer load and store instructions. Okay, load store single register. The single register load store instructions allow moving data between memory and an FP Neon register. This instruction can load store a byte, half word, single precision, double precision, or a quad word. The following instructions are used to load or store a single FP Neon register. The following instructions are used to store a single FP neon register. LDR, STR, that is the same as before. Load this register and store this. But I'm not providing what is the syntax. OP, I can say these instead of using R, instead of using X or W in front of the register number, and then the address. Uh, OP is either LDR or STR. Address is one of the register specifiers described in chapter 3, section 313 on page 61. The valid shift amount for the register offset mode depends on the size of the register being loaded. Hmm. Okay, name effect. Load gets the value of this memory address into this, and store gets the value of this register into the memory address. This load YT, where YT is any floating point register. Floating point register. Load value into the floating point register is store YT, where YT is in any floating point register. Okay, that makes sense. LDR get into the single precision, single word, single word, that is 32 bits from this place. Get 32 bits from this place. Load SY from address M0. Shit, that is too much sleep. And this does load the address of this and then add 8 to it, store this, and then store this. So store D4 using the address in V3, then add 8 to V3 to 3. And why 8? Because 8 bytes means 64 bits and double also means 64 bits. So I'm storing 64 bits, and thus after doing that onto the memory, I am incrementing the top of the memory by 64 bits. And then my mouse stopped working, and then there was light. Then there was Earth in the start. Shit. Let me do make my mouse work. That is crazy, it is not working. It ain't working, bro. Yep, it is. Back on track. Load store single register with unscaled offset. With unscaled offset. Just like this. And this one was pre-increment. These versions of the single register load store instructions allow moving data between memory and FP neon registers. Yep. These instructions can load, store a byte, half byte, and single precision double word or a quad word. That is, quad word is 128 bits. These instructions use an unscaled 9-bit offset. The following instructions are used to load a single FE neon register. Loader store unsigned register, load unsigned register, load FP neon, store to FP neon. Like this operation is either loader or store. Addition address is register offset. The offset is not scaled by the size of the data. So the value at memory location whose address is given comes to the Y teeth register and stores the value in the teeth register is stored in the memory location provided. And then we have this example load into the single byte, that is 32 bits from this point, and then store double word. Double word is 64 bits into the location whose address is in the third register, and then add 8, that is post increment 8 by 8. Stutter pre-increment, and before that store into the S0. Like after incrementing, store into S0. Then load, store, pair. The instructions are used to load or store two registers at a time. This can be useful for moving registers into stack or for copying the data. These two instructions are particularly useful for transferring data in a load store architecture because case instruction because each instruction can move twice as much information as the load and store instructions. Yes, because I am dealing with a pair, load pair, store pair. Well, that is what we normally do, and I can provide the registers that I want in this operation. These are the operands. Yep. And then we have address. A 7-bit pre-indexed po post-index or signed immediate. Address is a pre-index, post-index, or signed immediate. Okay, signed immediate XT. Range minus X200 to plus 1F8. WT range. That is when I'm using 32 bits, then the range becomes half, half the name. Load pair, store pair, and this happens. Load YT2. Okay, load registers from memory and then store registers from into memory. Load is store non-temporal pair. I think I should go and wash my face and then come back to the stream and also maybe piss. And frames have been dropped, and I'll just be back and Yo, the complete never dies. Yep, I am back. And here we are. This load store a non-temporal pair. What is, what is temporal pair to begin with? There are load store pair instructions which also provide a hint to the memory system that the data being accessed is non-temporal. Non-temporal data is data which is unlikely to be referenced again in the near future, such as streaming media, and need not be retained in memory caches. Oh, non-temporal. Okay. Load non-temporal. Store non-temporal. Load non-temporal pair. Store non-temporal pair. Non-temporal pair NP. Okay. Okay. It makes sense. So the data that I store or load according using these instructions which will not be cached, and that is good. Operation store 1, store 2, D1, D2, Q2. Yep, these are the values of the registers, and these are the addresses. Operation is either load pair, store pair, or I think load pair non-temporal and store pair non-temporal like this. And then address is a 7-bit pre-indexed, post-indexed, signed immediate. Address is pre-indexed, post-indexed, signed immediate. uh, Value of that value of a memory location is stored in a register. Signed immediate xt range for yep. If I'm using the whole range, then signed immediate this, and for a word it is half. Okay, in load I get the place from the memory into here, and in store I store from memory to there. uh, I'm getting into the YT register, the value at memory location address, and then adding to it size of address. Yeah, that makes sense. Data movement instructions. Okay, with the addition of all the FP registers, there are many more possibilities of how data can be moved. There are many more registers, and FP registers may be 32-bit or 64-bit. This results in several combinations for moving data among all of the registers. The FP instruction set includes instructions for moving data between two FP registers, between FP and integer registers, and between the various system registers. Moving data between data registers. How long is this chapter? I guess this was pretty long, right? This chapter, because they are essentially teaching assembly anew from the start. Nope, not that long, but yeah, this is good. Here I have all the instructions, all the new instructions at the end. And what does page mean? The page where they were introduced for the first time. Yep, yep. And yeah, that is cool. And then at the end, we must have exercises, which are also cool. Cool to do. Yeah, we got it. Page number 303. Uh, yep, here we are. 1, 2, 3, and with the addition of all, yep, moving data between registers. The most basic move instruction involving FP registers simply moves data between two floating point registers, or moves data between an floating point register and an integer register. The instruction is this: move data between registers. Move between a single byte This is the destination register and this is the source register. And ah, okay, here it is used S, and here it is we use W, and here we use S, because S is used in floating point registers and W is used in integer registers, general purpose, and X is used to signify we are using 64 bits in a general purpose register, and D is used to signify that we are using 64 bits in a floating point register. And we use X and D, which are different, to signify that X means general purpose and D means floating point register. The two registers specified must be the same size. Yeah. VDN refers. Yeah, what is this? VND and then 1 refers to the top 64 bits. Top 1 means second, right? And 0 would mean first, that is the LSB. VDN refers to the top 64 bits of register VN. Floating point move immediate. What the heck is this? F move dot F64 dot F 63. What is all that? Um, what is this? Um, dot F and dot 32. Dot F means floating point and 64 means 64 bits. And dot F is also here floating point and 32 means 32 bits, because this is single precision. This is double, therefore you use 64 bits. I guess. The floating point move immediate. The FP neon instruction set provides an instruction for moving an immediate value into a register, but there are some restrictions on what the immediate value can be. The instruction is F move, the same as this F move. Floating point move immediate, floating point move, the destination register, and floating point immediate value here. The floating point constant FP floating point immediate may be specified as a decimal number, such as 1.0 as a decimal number. The floating point value must be expressed as plus minus n divided by 16 into r, where n and r are integers such that n is less than equal to 16 to 31 and r is between minus 3 and 4 included. Minus 3 and 4 are included there. Okay. The floating point number will be stored as a normal binary floating point encoded with 1 sign bit, 4 bits of fraction, and 3 bits exponent. See chapter 8 and 8.7. Yeah, like the standard that we store floating point numbers. Note that this encoding does not include the value 0.0. However, this value may be loaded using move into SD, the value from WZR0 register. Hmm. The floating point number will be stored as a normalized binary floating point encoding with 1 sign bit, 4 bits of fraction, and a 3-bit exponent. Okay, and the floating point number must be expressible as this where n is less than equal to this and r is between minus 3 and 4. R is between minus 3 and 4. N divided by 16 into 2 power minus 3 to 4. Okay, okay, let's go with that. And then I can do F move, the destination register, and then my immediate value. Okay, okay, let's go through with this data conversion. And then when we are writing programs, we will get a better understanding, and or we can backtrace and get back here. Now, the ARM frame pointer provides several instructions for converting between various floating points and integer formats. Okay, FP versions also have instructions for converting between floating point and floating point formats. Also have F some FP versions also have instructions for converting between floating point and floating point formats. Okay, I can change the floating point format, but okay, like single precision, double precision, or non-IEEE standard. Convert between double, single, and half precision. These instructions for are used for converting between IEEE double precision, single precision, and half precision floating point. FCV floating convert between double, single, and half precision. So here, half is being converted to single, half to double, single to half, single to double, double to half, and double to single. So I can even convert higher number to a lower number, but that would result in lost information. Although the data processing instructions do not operate on half precision numbers, data processing instructions do not operate on half precision numbers. Okay, they may be used to store data in half the space required for single precision. Or, okay, they do not work in half precision numbers. They may be used to store data in half the space required for single precision, or one quarter of the space required for double precision. Hmm. Okay, even though these do not support half precision numbers, these instructions like this with when the destination register when the destination memory is only half, or this also, we can use these to store a bigger number into a smaller place with data loss, but we should know how much we should know how big the number is, so that we only move when we know that the data loss is only zeros, and thus there is no actual information loss. There might be data loss, but not information loss, I guess you could say. Convert floating point convert single to half is converted to single and then stored here. Convert half precision number in HN to single precision and store in ST. And the same for these. Convert from this format to the one on the right and store there. Convert between floating point and integer. Okay, and these are examples from double to single and from single to double. These instructions are used to convert integers to single or double precision integers to single and double precision floating point numbers, or for converting single or double precision to integers. F convert A to S. Okay. S single, signed, unsigned, signed, unsigned, signed, unsigned, signed, unsigned, signed, unsigned. Okay, and signed, unsigned, convert, and what is A? A. I'm not looking there. What A could be? Let me see what the others are. A, M, N, S, P, Q, Z, P, Z. I don't know. Convert float to signed integer, run away from zero. Convert float to unsigned integer, run away from zero. Run away. A is away from zero. M is minus maximum, rounds to minus infinity, and routes to even. N is somehow means even here, and P means plus infinity, and Z means rounds to zero. Okay, because we are converting from floating point to integer, we have to round at some place, and RA is run away from zero, and Z is run towards zero, round towards zero, and M means minus infinity, P means plus infinity, and N means even, rounded towards even number. And this convert single signed integer to float using C floating point control register rounding mode, and here I am converting integer unsigned integer to a float. Okay, that makes sense. And this is the format: signed unsigned and convert to float, and float convert to the mode and signed unsigned. Okay, the mode can be one of A, that is away from 0, M minus infinity, N even, P positive infinity, and Z 0. To specify the rounding mode, RD and destination register, RN can be any 64 with integer registers, RD and RN. FD and FN can be any single or double precision registers. Yes, but not half, single or double. Then I convert floating point, convert to this signed, and floating point convert to mode unsigned, and that, yeah, that makes sense and is understood. Now floating point convert AS, that is away from 0 into, and signed, and plus infinity and signed. Here I have away from 0 and signed, which is same as this goddamn register. Oh, but here I am converting that value and storing into, storing all of these values into general purpose registers. But when I'm converting integer to float, that is the only time that I'm storing from a general purpose into a neon register. It's 9.6.3 convert between fixed point and floating point. Fixed point and floating point, that is also crazy. I guess VFP3 and higher co-processors have additional instructions for used for converting between fixed point and single precision floating point. The ARM64 instructions are as this: F convert Z, Z was nothing. Z signed and unsigned. Convert float to signed fixed point. Z means fixed point somehow, and here also Z means fixed point somehow. And then here we have signed unsigned. Convert that to float, and I give it a fixed point FD. I have different registers for fixed points which start with F. Nah, what is the example? Yep, there is no FD, there is just general purpose registers which are used to store fixed point numbers. Data processing instructions. Wow. Yep, and then this, the convert instruction rounding off, and this also. FD and FN can be any single or double precision floating point registers. And then I have hash F bits, which is the offset. Why do I need an offset? Operand. It specifies the number of fraction bits in fixed point number. Oh, it specifies the number of fraction bits in its fixed point number and must be less than or equal to the size of the integer register specified. That makes sense. And yes, the usual thing. So now we are going through just the commands, and then we will be using those commands later in the questions. Data processing instructions. 1 hour 30 minutes. I have looked at time, or about 3 to 4 times, and that is not a good sign when you want to study. But what we have studied till now has been of acceptable quality, right? I'm not half-assing what I am studying. I am actually studying. Where did we start? We started. Now I feel like I'm goddamn stalling because I do not actually want to study this. We started here at page number 293, and we have come far. We are at page number 207, 307. Sorry, yeah, my bad. We did data movement instructions, now data conversion instructions, and then data processing instructions are the next big thing like AI. Instructions are provided to perform four basic arithmetic operations plus absolute value. Okay, negation and square root arithmetic functions plus absolute value. Four basic arithmetic functions and plus absolute values, negation, and square root. There are also special forms of multiply instructions that perform multiply accumulate. Okay, these operations will round a floating point in number to an integer. Will round a floating point in number to an integer. These are several options to control exactly how the rounding is performed. To know exactly how the rounding is performed. Okay, what is FRIINT? Round away. Uh, uh, Round using mode set in the fraction point control register. Minus infinity to m is minus infinity, n is to even, p is plus infinity, x is again round using the mode in floating point control register and raise an exception if the result does not have the same value as the input. If the result does not have the same value as the input, okay, z round towards 0. Fint, what is fint? What the heck is fint? Round to integer. Oh, these are only for rounding. Fraction round to integer. Yes, okay, that makes sense. Fraction round to integer, and there are multiple ways that I can round. Yeah, I can round away from 0 towards 0. I can round according to FPCR register, then minus infinity, plus infinity, even number, or according to FPCR. And if the input and the output values are not same, then I will raise an exception. That is X. X means exception. And then here is the syntax. Fraction round to integer, and then the option FP destination and the source registers must specify either two single precision registers or two double precision registers. Two single precision registers or two double precision registers. Okay, operations here, and here is the example: absolute value, negate, and square root. That is crazy. Fractions, absolute value, fractions, negative, and fraction square root. Square root is actually crazy. I mean, literally, if you have hardware designed specifically to find a square root, that is, I don't know, that this seems like too luxurious of a thing for any human to possess. I feel like actually using it would feel like an Egyptian pharaoh, right? Your hardware is designed to find out the square root, and you do not have to implement the algorithm using plus, minus, multiply, divide, basic operations. That is literally crazy. Like, I did not do anything, it was not me. Spare me. FT destination and source must specify. Yeah, yeah. Yep. Same as above, so below, and that is Okay, destination register, I can find out absolute value, negative, and square root of numbers like this. Absolute value, negative, and square root of floating point numbers. That is crazy. Add, subtract, multiply, and divide. Finally, the juice. The basic mathematical operations require two source registers and one destination register. There are five basic mathematical operations. Five. Add, subtract, multiply, multiply and negate. Find the multiply and then negate. That would be equivalent to multiplying when one of them is a negative number, and then divide. Okay. F, add, fraction, subtract, fraction, multiply, fraction, negate and multiply, and fraction, divide. And here is the syntax. Fraction, add, multiply, divide, negate and multiply and subtract. Destination register and two source registers. Option is one of these, and these registers must specify either three single precision registers or two double precision registers. Three single precision uses 32 bits. Uses 32 bits, and since these registers are in total 128 bits, I can fit in four single precision registers. Oh, oh, my bad. This means one is this, two is this, and three is this. So like three registers. I have to specify three registers here. That is cool. And these are the basic examples. The thing that we have been doing during this whole series. Now it is just with floating point numbers with an additional f added at the start. Then multiply and accumulate. Special multiply instructions. These instructions are used to multiply and accumulate the results. Fused multiply, accumulate, this option. Wait a minute. Yep. Oh. A fused multiply accumulate operation does not perform rounding between multiply and add operations. These instructions are used to multiply and accumulate the result. A fused multiply accumulate operation does not perform rounding between multiply and add operations. A fused multiply and accumulate operation does not perform rounding between the multiply and add operations. Okay, it does not perform rounding. That is cool to get a precise result. The two operations are fused into one. The two operations are fused into one. The two operations are fused into one using the fused multiply accumulate. The two operations are fused into one. Okay, using the fused multiply accumulate can speed up and improve the accuracy of many computations that involve the accumulation of products. Neon provides the following fused multiply accumulate instructions. This fused multiply accumulate and FM add, fused multiply, subtract, fused negate, fused negate, multiply, add, fused multiply accumulate, fused multiply accumulate, fused multiply subtract, fused negate, multiply, accumulate, and add, multiply and accumulate, fused negate, multiply, and then subtract. Good. We have to give four registers to this thing. A destination register like this, and two source registers, and then a accumulator register. Must specify either four single bit precision or four double precision registers. OP is one of these. And what does this mean? Yep, accumulate register is added, subtracted from, negated, or Yeah, negated. The operation can at the end be negated. Multiply the values in the operand registers and add the values to the destination register. Multiply the values in the operand registers and subtract the value from the destination register. From the destination register or from the accumulator register, and then store it to the destination register. Then multiply the values in the operand registers like that and add it to the accumulate register and then negate the result. And here I have multiply the values in the operand registers, subtract that result from the accumulator register and then negate it. That is cool. That is cool. Okay. And here I have FMLA. Fuck my life also, I guess. FMLA and add the values in these two registers. Multiply the values in these two registers, then add this value to their product and save it to this. And same goes for this. Now we have min and max operations. The min and max operations compare two registers and set a third register to the minimum or maximum of the two values. The instructions are this. Okay, that is crazy because in normal general purpose registers, I would have to do this by compare select. First, I would have to update the program state by doing a compare and then conditionally select a value based on that. F max, F max number. Okay, max is different from max number. That makes sense. Min is different from min number. And here the operations F max, max number, min number. And before min, they forgot to write F in here. That is okay. Maximum, what the heck does maximum number mean? What the heck is maximum number? Okay, yes, here is the explanation. If D and must specify either three single precision registers or three double precision registers. If one of the two value is nan, then F max number and F minimum number returns the other value. Okay, if one of them is not a number. If either of the two is a nan, and then Fmax and Fmin return nan. If both values are nan, then all of these instructions produce a nan. Like, of course, yep. And then I have the equality table. Always equal, not equal, greater than equal to, less than, greater than, less than equal to, high, plus, carry some, or, okay. This is something that I will have to get into and understand more clearly. Condition code for meanings, and yep, here is a compare and this refers to this. Now, yep, compare. I think we got this today. Maybe not. Maybe not. Okay. And the main thing is, okay, we have to complete till here. And what is this? This is performance comparison. This is page number 317, and we are currently floating point sine function. We are currently just here. Oh, maybe we have got it, and the time is 10 minutes. Not enough if we only continue this stream for the next 10 minutes, but we got this. We got this. The compare instruction subtracts the value FM in FM from the value in FN and sets the flag in the P state register based on the result. The condition code menu after an F compare float compare instruction are shown in table 9.1. Compare with exception, compare with positive infinity, conditional compare. Okay, C conditional compare with exception. That is crazy. Okay, I can floating compare with E, an option E means exception, or I can conditionally compare. And in normal compare, I provide two registers and an offset for the second register. And here also same. But in conditional compare, I provide an immediate some value and then a condition due to some reason. Yeah, condition I get, but what is these? For the F compare, F compare and F conditional compare instructions, an exception is raised if any kind of nan is encountered. Otherwise, an exception is raised only from signaling nans. Okay, condition is one of two character codes from table 3.2. Yeah, and only two, only like where I have a lot of them, I can only choose one of them, which consists of two characters. Okay, and condition yeah is unsigned immediate 4-bit value is a value to set the V flag if condition is not true. If condition is not true, then I can set the V flag. That is also crazy, yeah, of sorts. P state compare eh, uh, negates compares two registers compares to 0. If the second register is 0, then compares to 0 and sets the P stake. And if condition is true, then it compares, and otherwise it if the condition is not true, then it puts this immediate value into the P state. And same here, except here it compares to 0 if the second register is not given. Compare this and subtract the contents of the first from the 0 and set the NZC flag. -0 carry overflow flags. The conditional select instruction selects a value from one of two registers and based on the given condition stores it in the resulting register. That is the same as we have been doing in general purpose registers. Here I have the destination and two registers and then a condition. These must specify three single precision registers and three or three double precision registers. Condition is one of two character condition. Yep, provided in table that above table. Oh, they have a separate table for this. Table 9.2, 3.2. Oh, like way back. And now we are at chapter number 9, not chapter number 3. We have come quite a way at 350 pages, 15. And then operations. Condition select. If the condition is true, then I get the values of this register into this. Otherwise, if it is false, then I get the values of this register into this register. And here is an example for the same. Floating point sine function. Sine function is crazy. A fixed point implementation of the sine function was discussed in section 8.6, which I did not read, and shown to be superior to the floating point sine function provided by GCC. Okay, now that we have covered floating point instructions, we can write an assembly version using floating point that also performs better than the routines provided by GCC. Okay, so in this code, we are going to write our own code that finds out sine for a given number, but that code and the special thing about that code is, first of all, it uses the vector instructions, and second, it is faster, more optimal than the one provided to us by GCC. Why? Well, GCC is GNU C compiler. It is a general purpose compiler. It has to look for a lot of things. So at times it can be slow, but those are rare, but it can be slow at times. Listing 9.1 shows a single precision floating point implementation of the sine function using the ARM floating point neon instruction set. It works in a similar way to the previous fixed point code, there is a table of constants, each of which is the reciprocal of one of the fractional divisors in the Taylor series. Okay, we are implementing the Taylor series for the sine function. Taylor series. Ah, shit. All of this is crazy technology that we can just solve a series and we will get a value, right? Take, we can take, uh, what do you call it? When multiple sine waves are added and the resulting non-patternistic wave that you get. Oh, is it? Does someone know in the chat? No, of course. I am the only one watching. Um, uh, what is it called? It is not superposition. And the wave which we give to a Fourier series, and we can find the individual things, the wave which we give to a Fourier series, and we can find the individual wavelengths of the sine functions that were used to create that homogeneous. What is a superposition of waves which is solved by Fourier series called, what is it called? Linear combination Fourier idea, Fourier representative, um, superposition of waves called superposition. Yes, that is just superposition. It is only called superposition and nothing else. I thought like homogeneous or something. Okay, but that is not the thing now. The subroutine calculates the power of x one by one and multiplies each power by the next constant in the table, summing the result as it goes. Note the single precision floating point version uses fewer terms for the Taylor series than the fixed point version. This is because there are fewer bits of precision in the IEEE single precision format than in the fixed precision format used in the previous chapter. Okay. Simple scalar implementation of the sine x function using IEEE double precision. Okay, this one uses double precision values and this one uses single precision. And then what we have? This 9.2 shows a double precision floating point implementation of the sine function. Single precision floating point implementation of the sine function using the ARM FP neon instruction set. Again, there is a table of contents, each of which is the reciprocal of one of the fractional divisions of Taylor series. The subroutine calculates the power of x one by one and multiplies each power. And okay, this is just explaining how we can calculate a sine function using Taylor series. And I guess I will come back to it at some point and understand how we can calculate sine function using Taylor series. But now, for now, we are almost done. Table 9.2 shows the performance of different implementations of the sine function with and without compiler optimization. The single precision CE double. Okay, what is this performance of sine function with various implementations? Optimization none and offset. Okay, with this tag on. When we don't have the tag on, then single precision scalar assembly. The speed is this with single precision C with the GNU compiler. The speed is this, so 3 times faster. With double precision, it is a little bit more than 2 times faster. But when we are using a optimized version of the compiler, the results with single precision are as good as 3 times faster, a little less than 3 times, but in double precision, it is a little less than 2 times. That is good. That is good. The single precision C and double precision C implementations are the standard implementations provided by the GCC GNU-C compiler. The comparison tests were performed by timing each of the four cases on the same set of 100 million random numbers with and without compiler optimization. So that is a good test if you are using 100 million random numbers. When compiler optimization is not used, yeah, and this just explains this. Now, in every case, the assembly version were significantly faster than the functions provided by GCC. It is clear that writing some functions in assembly can result in large performance gains. One interesting thing is to note is that without optimization, the single precision C code is actually slower. Without optimization, the single precision C code is actually slower than the double precision code. This is because when optimization is not enabled, the C compiler converts single precision to double precision numbers before calling the sign function. When optimization is enabled, the C compiler uses single precision version of its own sign function for single precision numbers. Okay. And then here I have a list of all the instructions that have been explained in this unit. And then chapter summary and then exercises. We will be doing these exercises, completing all of these exercises tomorrow, and then moving on to advanced SIMD fucking instructions. For now, the AArch64 FP Neon coprocessor adds a great deal of power to the ARM architecture because uh, this gives us dedicated units to do single instruction multiple data things and for doing floating point arithmetic. We can do floating point arithmetic with the FP unit and SIMD instructions with the Neon unit. And in generally, ARch64 FP and Neon coprocessor is the same. They are one and the same unit, and they are embedded in nowadays. We do not have a coprocessor that is separate from the main processor. Instead, we have a unit inside the processor itself that is used to implement the FP Neon instruction sets. And the ARch64 assembly has been extended so that the main processor, the general purpose processor control unit, can be used to perform instructions on the Neon FP unit. And that is crazy. The FP Neon register set can hold over twice the amount of data that can be held in the ARch64 integer registers because ARch64 integer registers are 64-bit registers and FP Neon registers are vector registers and are 128-bit long. The additional instructions allow the programmer to deal directly with the most common IEEE formats for floating point numbers, that is single precision, double, and quad. In next chapter, we will see that the ability to treat groups of registers as vectors adds a significant performance improvement. The GCC compiler does not make good use of these advanced features, which gives the assembly programmer a big advantage with high performance code is needed. Okay, in this chapter, we came to know how we can use the vector registers for performing floating point things, right? All of these are floating point instructions and moving instructions to move things from integer registers to the floating point registers, to the vector registers. In the next chapter, we will be learning about how we can use them to do neon instructions, that is single instruction, multiple data types, multiple data points. That is, we can do addition on 4 pairs of numbers simultaneously at the same time. That is crazy, and our hardware is dedicated to do that. That is our FP Neon unit. That is crazy, and well, in the next chapter we will learn SIMD instructions. But now we will do exercises. We have about 10, yup, 10 exercises. And how much of the book is left? Let me see. Uh, we are, let's say, at page number 320, and this is this that is part of the chapters. I can go to the index or directly. I'm stupid. Yep. In the index, we are currently at the end of chapter number 9. Then we have advanced SIMD instructions, which is about 80 pages long and is going to be amazing. Of course, amazing. And then we have devices, how we can access the peripheral devices in assembly. That is also crazy, amazing. Then we have chapter 12, running without an operating system. We can run our code without an operating system. Okay, that is going to be amazing. Yep, that is going to be it for today. And bye.